Swayam Prabha. Digital India. Educated India.
So, I mean, this was to motivate you, but I can now write random things. I can write many examples, but I'll give you one more example where I won't tell you where it comes from, or maybe I'll tell you, but okay. So, I don't know. Okay, so the binomial distribution is that the set, the values it takes is 0 up to n, and p of okay. The second thing is what I'll call the Poisson distribution. You will find a lot of names in both physics and mathematics coming from their French names. That's because they have, French has a very rich history of maths and physics. And so Poisson is such a name. Also means fish, the French word for fish. So Poisson distribution is that now the set is the natural numbers, include 0. Okay, and there is a parameter lambda, which is just some positive number. It's some real number greater than 0. Okay. Okay. Maybe next lecture we'll see how we could, there's a nice particular way to go from this distribution to this distribution, but we will do it as a physics way because there's a physics meaning to the whole thing. Okay. So, is this clear? And I'm just giving you the probability. I don't need to, you can see I freed myself of where we started. It's a good thing. Okay. Now, a question to you is we need to still, we can do one check. Does anybody know how to prove this? Because I don't know what you people know or don't know. So let's try to do that. Okay. So e power minus lambda is common, so I'll just pull it out. If this is for this to be equal to 1, this should be, what should this be? E power plus lambda. Absolutely right. So either you know this identity or you don't. Do you know? Okay. If you know the identity, yes. Or you take this as given to you. Okay. So this is equal to 1. Okay. And this is a remarkable formula actually. And if you know any derivatives, if you know anything about derivatives, okay. So one simple check is that what is d by dx of e power x. Okay, it's a unique function which, if you take its derivative, it gives back itself. That's not enough. I have to give one more condition, and its value at 0 is 1. Okay, so we can check at least if this formula I've given you is correct. Okay, there's a technical requirement which a mathematician will say, but I'm not. So I will peacefully do this. So I'll just take so let's do d by dx. What is d by dx of x power n? So let's do that. So let's do this. So first thing I'll do is, if I have I can use the fact that derivative of sum is equal to sum of derivatives. Okay, so I'll do this. And this way the mathematician will complain. For finite sums it is okay. For infinite sums there's a technical requirement called convergence, which is there in this case. So, but physicists, what we do is we do all this, what is called Gödel or Golomb. We exchange this order, assuming if it if it works, it's good. If we mess up, actually it's very interesting. That's why we are okay with doing that. So we freely do this, but in this case I'm allowed. So d by dx of x power m, I'll jump one step, is m what is m times m factorial? And the key is that the 0 term is 0. So this will just become so I can shift and call some m tilde, which is m minus 1, m prime, or so let's just call this m prime is equal to m minus 1. So when m is 1, m prime is 0, so on and so forth. So this is equal to proof. Physicist proof that that formula at least it makes sense. Right? You agree? We got back the same summation. So it satisfies this property. Okay. So at least this is a way of understanding, even if you didn't know. Okay. So this is a really cool thing, requires this identity. Any questions or comments? Yeah. No, you don't have to worry. It's working in our case.
No, for x equal to 0.
What?
That summation of e power x, right?
Yeah, but d by dx, a function and its derivative have no relation. Value of a function and its derivative at that point have no meaning. Because if you say f of x equal to 3, what can you tell me of f prime at 0? What? There's no meaning. Because derivative requires at least 2 points and then take limit, right? If you talk second derivative, I need 3 points at least. So on and so forth. Okay, so that's no meaning.
No, I thought like...
No, but this doesn't violate anything. So we know that I told you that function has the addition property that at x equal to 0, but m equal to 0 is x power 0 by 0 factorial. So it's 1. So if you expand it, it is 1 plus x. So it agrees with what he has. So you put x equal to 0, the first term
is 0 power 0, right?
It is not 0. 1 is 1.
No, like if we look
X
at that
sequence. X power 0 is 1. X power 0 is 1.
If we put x equal to 0, so e power x, e power 0, so 0 power 0 will come, right?
No. Please don't do that. Okay. So if you want, you can write this definition. I could have written it as m equal to 1 plus x. Okay. It's valid for all x. You can't just... what you're doing is real faux pas. Which is to say that the value of the function at some value. X power 0 is 1. So you take it to be this expansion. That's the mnemonic. It's not 0 power 0 is. Now I'll be a little bit more, here it was only discrete values. I'll be more brave. I will take values that x can belong to all real values, continuous. Okay? But now we have a problem. It's like here we are able to assign numbers to this thing. So, but what we would like to do is, so this is the real line, say, if you pick a particular point, it is set of measure 0, it is nothing, it has no support. So you can't assign a probability. I mean, you do not want to assign a probability, but you want to assign a density. So what you do is pick a point x and pick a small neighborhood of that point, delta x. And then I will introduce this function p of x delta x. Okay, I'll define it for you, is the probability of x taking values in the region don't worry, closed open intervals. Okay, so I have to define something like this, what it takes. Okay, so what we do in a physics way is we don't call p of x the probability, we call it density, probability density. Because if you pick a point, you can see delta x is 0, so that becomes 0. So if it has no support on one, you need to have some neighborhood. Further, now we want to say total probability should be 1. How will you write that? So you would have written summation over m. So instead, so 1 will be equal to, I'll call this dx now. This is again a physicist way. Total probability should be 1. And so what you do is, what I have in mind is I break it up into really small intervals and do this. That's the definition of integral, right, in some sense. Okay. So p of x will be some positive function. It will always take, it will be positive, but such that this is the same statement as saying total probability equal to 1. Okay? Yes.
Sir, is it fine to write dx p of x, or should we always write it as p of x dx?
I am not a mathematician. I don't lose sleep over. I write it both ways. Mathematicians write it, I think, as p of x dx.
Thank you.
Okay. I mean, you have to appreciate, I truly appreciate the precision of mathematicians. They're very, very precise. They define things properly, but physicists, we are a little bit loose. So I like I said, I do p of x d of x dx. I mean, the reason I like this, I haven't argued with my math colleagues, is that suppose I have two integrals, dx and dy, and I want to put limits and also I'd like to say which one goes with which. But they will say, no, there's an ordering, so they will do that. So I prefer this, but yeah, you're right, I should write it like this. The precise way to do is this. Okay. So I'll give you one more example, but this time from this setup. Okay. the Gaussian or the normal distribution, and it has two parameters. Okay, and the values are in real. Okay, so I just have to tell you don't get scared by all these things. Okay. So for simplicity, we could set x equal to 0. Okay, so then it looks like e power minus x square. So this function, if you plot it, it's called a bell curve because it looks like a bell. Okay. See, you can see as x goes to x becomes very large, large and positive. This becomes e power minus of some large number which goes to 0. If x goes to minus infinity, x square still goes to some large positive number. So it goes off to 0 and its maximum value occurs at 0. I put mu equal to 0, but its maximum value will occur at when this becomes when x equal to mu. So I could have replaced this with mu if you wish. It takes its maximum value and okay, so these factors here are, by the way, this proving that integral p of x dx equal to 1 is a non-trivial integral. Okay, it's not a simple integral. It cannot be done by any elementary method. There is a trick. So, and that trick is just like, it's like, you know, it's like a trick which works for only one case to do this integral. So let's not worry about that. So, but it's just a claim. Okay, it's not something which we know. Why am I giving this? What is special about this distribution? So, for instance, I could be taking an exam, or you are taking an exam. There are many people taking the exam. Okay, so each person is like a random variable. Rather, the marks they take is a random variable. And what you want to ask is what happens to, how will the marks be distributed? Okay, so these terms have a meaning. Mu is called the mean. Again, these things you know from statistics. Sigma will be called standard deviation. Okay, but what are these things? I want to define that. And so what it says is that if you have it's called the law of large numbers. Okay, so each of us think we are very, very individualistic and yeah, I will do my thing. But as a group, we are sheep in some sense. We will all conform with this distribution. Okay, so for instance, if I'm teaching the first year course, we have like 1,200 students. Of course, marks are between 0 and 100, so it's a little bit, this is artificial. It won't go to minus infinity to plus infinity, but nevertheless, you will find that this is a very good approximation to the distribution of marks. Okay, so there is something called, I will not prove this, something called amazing theorem, which you may understand maybe 5 years from now, but it's worth knowing that there is a theorem which is central limit theorem, which says that under certain conditions, if you add a bunch of variables, independent random variables, they distribute, even doesn't matter what you choose. they will end up becoming a normal distribution. There are some technical conditions, but it's pretty good. But this will also come in my physics exam in the next lecture. Okay, so now that I've given you 3 examples, how do we compute with them? I will no longer distinguish between whether I have discrete or continuous. I'll just use random variables. Okay, so I will define these 2 things for arbitrary random variables. Okay, so only thing to remember between continuous and discrete. For discrete, you do summation. For continuous variable, you do integration. Okay. By the way, you can have hybrid situations where part discrete, part this also can happen. Okay, but we won't worry about that. Okay. So now, so let's say that x1 and x2 okay, and say or let's say x and y maybe. Let's do x and y. I hope you are seeing my notation, right? Capital letter for the variable and lowercase for the values. Okay, so P of x, y will be the probability of the first variable taking x and the second variable taking y. Okay, and let's also put this subscript to remind us what is the random variable. Nothing, yeah.
So both of them happen simultaneously or?
It doesn't matter. It doesn't matter. They're just 2 random variables. That's all. I'm not even saying if they're independent of each other. Nothing. We've not said anything. Okay, so this will tell you the probability okay, that's all. And of course, sum over all possible values of x and sum over all possible values of y should be 1. We know that. But now the question to you is, suppose I told you x and y are independent of each other. Okay, so let's say that if we just looked at x, I can assign a probability, which I'll say px of x, and here I'll call it py of y. So if I was just looking at only variable x, I can assign probabilities. Right? That is just close this. This is the probability of assigning to every guy. Close this, I get this. Is there any relationship between these 2? In general, no. But if x and y are independent of each other, the fact that I know x will not influence this answer. Okay? This is equal to this. We already use this in a complicated, for n coin tosses I did that, right? I just multiplied the probabilities. But this is just a case of 2. Just a little bit souped up, but it is the same argument. Okay? So this and these 2 are not necessary, there's no relationship between them. If x and y are dependent on each other, there is some overlap. All I'm saying is that there might be extra features. I'm not interested in that. I'm interested in this case. Okay, but yeah, there are properties. I mean, I'm not even thinking about what you said, so I won't answer it because I might say something wrong. Okay, so is this clear? So if they are linearly independent, this happens only if. Okay, so now that we have a sort of, suppose we have then n linearly, n independent random variables. Again, the probabilities, if they're independent, would be the product of their individual things. Good. So now I want to just define two quantities. What is the mean? So let's just x is some, it's a random variable, and I want to define what is the mean of x. Mean of x. Does anybody know how to do this? You take all the values and weight it with okay. I'll use some notation. I won't call this because more generally, if you give me some function of x, any function, okay, or let me not do this. So this is definition. Okay, some books also use the same thing. Expectation, read this as expectation value, what you expect for x power m, and that you just put x power m here with this, with that probability, and add all possibility. So also the other, I won't use this notation, this is a physics notation. Okay, so this is nothing but okay. Just remember that these are numbers. All these are numbers. Any expectation will be a number. Okay, so now I will define certain. Is this definition clear? Yeah. No, this is just telling you what is the probability that you can get. So what you're doing is you're tossing the coin and you're asking what is x power m. So if you got, so let's say we're doing x cubed. So let's say you got 3, then you will say I got 27 because I'm doing 3 cubed. Whatever number I'm getting, I'm cubing it. If I got 5, I will cube it and get 20. But then what is the total answer? This which each probability you weigh, it's weighted by the probability. Yeah. No, here m is fixed. There's a particular value of m. So no. So I can have things like this. I can do something like this. 2x square plus 3x. I'll take something more complicated. What it says here is that you do this. So put little x now, 2x square. You don't, the weight is the same. But now you can see that there is a nice property that this is nothing but okay.
In the second case, when we do 2x square plus 3x, how many trials of x do we do?
No, this is, I mean, this is saying mythical thing where you take it, we've given the probability, we do infinite number of things, it will converge to it. What we will get. Okay, so hopefully this definition is clear. Okay, so then we can define okay, so suppose I have two variables z and x and y. Okay, So now, what this means is that if y took value little y and x took, z will take little z. Okay, so that's what it means. And we are going to assume that these two are linearly independent of each other. Okay, so what we want to say is that, okay, so one more thing to remember is that if we know the probabilities of x and y, we know the probability of z. Okay, so what it says something like this, right? It's all positive. I mean, there can be more than one solution to x plus y equal to z. All the solutions, each one, the probabilities, they add up. But there's something very nice that happens, which says that, suppose I want to get expectation value of z. Okay. This has to hold. So let's understand this a little bit. What it says, so let's look at this. This expectation value of x, it just says that you, it only depends, this is independent, this guy is completely independent of y. Yeah, my mistake. Totally wrong. Okay. So this you can check. This is easy to check. You know that the probability, I mean, this is always true. Okay. But suppose we wanted to do z square. What is z? It is x plus y whole square. I will write, I am jumping one step, but I will explain to you now. So it's similar to the thing, I just add these, you add these guys separately. But you have written expectation value of x and y, but x and y are independent of each other. So it will be equal, it's equivalent to writing this. So here I have used linear independence. Okay, but now this is ugly, they don't add. So if you know expectation value of x square, expectation value of y square, it doesn't give you z square. It doesn't add. So you want a quantity of the variables x and y which will add. X square doesn't work, but something else works. Okay, what works is, so I'll keep this, I want this. So I just wanted this, that's all.
That is, if we define z as x.
Yeah, I'm only looking at z of xy and I want to find quantities of z which will be equal to the sum of the quantities of same quantities in x and y. Yeah.
Sir, over there we have written z square's expectation value is equal to x square plus 2xy plus y square, the whole thing's expectation value. Shouldn't it be like z expectation value the whole square, like the other way around?
You can go ahead and check that my formulae are right. You can check that.
It's like the summation,
Yeah.
right? That's why I'm
So
asking.
no, yeah, but it will simplify. It will just separate out nicely.
Is it? Okay.
It will work out. Yeah. Yeah. Mike.
So, doesn't that final statement only stand if neither x nor y are not equal to 0?
So the only this, if x and y are not independent, this part is wrong. I can only write xy.
No, she's
Okay. So this is where only this term will, so the cross terms cannot be separated and written. Only when x and y are independent of each other you can do that. Okay. So now can we improve on this? Can we do something? And so what we will do is we will define sigma x square to be okay, which can also be written, this is also the second way of writing it. Okay, so this quantity is called variance of x. Okay, it's called variance of x. Its square root is called standard deviation. Okay, so nobody tells you why this why not 2 times this, why not, so this formula is kind of a cheat. I'll tell you why in a moment. I'm removing the mean and then looking how it, that is true, that's correct. But what is cool is that variance adds, not standard deviation. Square of the standard deviation adds. If x and y are independent, so now we have a property of x, property of y, which adds. So x square by itself is not additive. This is also, and so you can play with it. You put a number here, put a, and try to ask what is the value of a such that it will, this property which I am demanding will be satisfied. Okay, so there are actually for every, if you notice, everything has power 2 in this, roughly counting powers of x. Okay, 2, 2. So we can go to cube and ask what is it. Okay, so we'll form some notation. So
Sir,
1 second, I'll just write something. Yes. Somebody.
sir, so by that is minus 2x expectation 0.
Which one?
Is 2x expectation 0 or
This is just expectation of x is a number. Take that number and square it. It's the square of the mean. But this is expectation of x square. It's not equal to this. These two are not
so
equal
it
to
is
each other.
defined as to be equal to x minus x expectation square, or how can
This
it
is
be proved?
definition of this quantity.
How can we prove the equality?
This.
No, the
This one.
next yeah, this one.
Oh, you want to prove that. Sorry. That's not hard. You just expand it. This is just a number. Okay, so let's do that. So let's just, since it's a number, I'll call it mu. Expectation of 1 is just sum over probability, so this is 1. Okay, but this is what? Expectation x, which is mu. So you get minus 2 mu square plus mu square, which is minus mu square. It's an identity. Thanks for asking. That's an obvious thing. So these go by the name of cumulants, and there's different notation for that. Mean is also called the kappa 1 of x, which is the first cumulant. There is second cumulant. There was by mistake, there's a 2 there. Okay. So now you think, I know the answer in general. No. Life would have been nice, no, if this was true. No, it's not. So there's a whole infinite list of this. Huh? Huh? Why? So you do this, right? You write the most general set of terms which you can. So how would I do, say, cubed, right? I don't do it this way. I'll write something like this. I'll start with x cubed and I want to make it work. So I'll just write some a times. Okay, this is one term. The next fellow can be b times. These are the only possibilities. And I will ask, I'll go and put this requirement, choose A and B such that if that property holds. And I claim that there exists a solution and this is the solution. So it is not obvious, nor is there, I mean, there is some fancy generating function way of writing it, where you can get all of them in one go. You combine the infinite set and do something. But don't worry about that. So you can, actually I really enjoy, checking this, whatever I claimed, right? So what I'm saying here is that kappa this property is true for all of them. But from your viewpoint, it should at least tell you, remove the mystery behind this minus sign. Why is it not minus 2x square minus 3? This is the only guy which has this property. For mean, it's like boring, nothing happens. Whether independent, nothing. Okay. Kappa n is this, all of these. There are infinite set. I have given you first 4. No, it doesn't. Oh, this formula breaks down at 4. It gets more and more complicated. Personally, I don't even remember this 3. I looked up. I went to some cumulant I put on Wikipedia and got. I don't remember this 3. What? Here, I've defined it for you. So you start, you do kappa 4 of z you put in, and then you write z equal to x plus y and do binomial expansion, expand it until you go blue. But the takeaway is not the precise numbers, but this property. Yeah, no, someone need not, you can do it in your room. Yeah. Yeah, so we call this the 4th cumulant, etc.
Yeah, so is the definition of the nth cumulant of x like the expectation of x power n minus expectation of x whole power n? Or
No,
what
no.
is the definition of a cumulant? Then?
It is that thing which has order, it is made up of nth order powers of x power n and stuff, all possibilities, such that this kind of property holds. This is the defining property. So I'll just say, I'll write something plus other terms.
Basically, if z is defined as x plus y, cumulants are defined such that that statement holds. Okay. We calculate based on that.
Yeah. But you can see that the cumulant is defined independent of whether it's the independence, etc. It is this particular property which singles out these combinations. It also tells you why standard deviation. What I want to tell you is that standard deviation is the first of an infinite set. Mean is kind of boring in some sense. Mean is the first actually. We call it the 0th maybe. Really, this is why we define. Okay. Now let's think of this guy. This is a very interesting distribution for which all the higher cumulants vanish. So kappa 3, kappa 4 onwards, everything is 0. This is equal to sigma square. This is equal to mu. Yeah.
So we've been using like a lot of squares and stuff on sets pretty much. Like it's just a set of events, right? That capital Z, capital
Yeah,
X, capital Y. What do you mean by square of a set? Actually.
It's not square of the set, it's square of the random variable. I don't want, I've gone away. I mean, the whole idea of a random variable is you go away from the sample. It is not, I mean, it's set of values.
It's a set of values.
Yeah, the value, those are measurable values. Heads is not measurable.
But
Number of heads is.
Okay.
Okay, so I mean, there is some, so what is happening is that you're going to random variables, it frees you of being stuck to a particular realization or something and gives you more freedom. Okay, so next lecture we'll do some physics and we will use all this. Okay, so we'll solve two problems using these ideas. The first one is how, so you have a gas of molecules in a room and I want to ask what is the distribution, if I go ahead and pick some small thing, what is the distribution of how many atoms are there or molecules are in that little volume? That's first question we will answer. The second question is we will answer is you're given a gas and I'll define something called equilibrium. What is the distribution of the velocities? Okay, these two things we will just answer. And the key beautiful thing is we can answer it at your level. Okay, so we will do that in the next lecture, which is Monday, I think 9 a.m. I'm the opening batsman, right? Okay, so see you guys on Monday.